So this is problem 7 from chapter 3 homework. So right here on the block diagram, we have a for loop, or a while loop that's in a for loop, and this actually referenced problem 8 from chapter 2, so this is where most of this formula comes from. But first of all, we'll say we have a million wired into n, so we'll run a max a million times, which is just what the book told us to input. But okay, so here we have a random number generator from 0 to 1, and we're timing it by 10 because we wanted random numbers from 1 to 10. Then it'll go in and round to the nearest number up toward plus infinity. So essentially, if it's a decimal, it's going to round up to the next greatest integer. Then here it checks if that value is equal to 5, and if it is, so if this value comes out true, the program should stop. Then if we come down here, we have our I value, and it's I plus 1, which runs into this numeric indicator, which is the required iterations, and there's a plus 1 because it's not likely, but it can happen on the very first iteration, even though the I value is going to be equal to 0, so we just want a 1 to come up just so we know it at least ran one time. But this value from I is also taken out, sent through the while loop and the for loop, and it indexes, so it sends all the values that I went through, and it's wired into a mean function, aka the average, and then that mean value is displayed on a numeric indicator. So the last one we ran 4, but if we run it, we'll see. So it took 11 iterations, and this is essentially what you can expect it to take, or the chances, I guess, of getting 5. And since this value is really close to 10, that kind of makes sense because our random number generator, it's 1 out of 10, so there's 10 possibilities, and to get 5 is 1 chance, so this 10 value kind of makes sense. We'll run it again, get 6, and see, it's still close to 10, but this time it's a little under. Yeah, this is problem 5, and on to problem number 9. Okay, so yeah, this is kind of a big one. So this is the integral of VI, the numeric integration. So up here we have our range. We have 1 minus 0, and then this is our dx as well, which is on a numeric indicator, or control, sorry, which we can control from over here. And then the range is divided by the dx, and then this is another round to the positive infinity, just so it's an integer, and it's wired into n, so this kind of determines how many times we're going to run it. This 0 is then wired into this for loop, and it splits into 2, so it comes up here, and it's plus whatever dx is, and then runs into here, and this is a what's called a shift register, and essentially that means it's going to run back to here over and over again, and every time it's going to add the dx, so we're going by, this is our step size, so this kind of makes sense. And then the value is sent into this x squared, and then 3 times x squared, which is just the function we were given. And then that is sent out into this integration VI, which takes the integral of it, and also our dx is wired into the dx value for this. And then that comes over, and the integral value is displayed on this numeric indicator, which is that one. And then the integral value is then wired down, and this is essentially the formula just to find the percent error from our actual. So it's just 1 minus our integral value, and then it finds the absolute value and divides it by 1 and multiplies it by 100. And then of course it's wired into a numeric indicator, which is right here. So if we run it, we should see that we get an integral value of 0.99, almost 1, and then our percent error is 0.029, so about 0.03. And that's essentially how far we off from our actual value. And we can, if we run this continuously maybe, and then we could take away a 0. And you see, oh wait, let me click out. You see how it changes. And yeah, this is problem 5.